So, hi everyone. My name is Lucien Gauchet. I'm working at the Observatoire de Paris, developing an interferometer, working in the infrared, in the H-band for the detection of odd Jupiters. The specificity of this interferometer is the use of the recombination of integrated optic recombination. Here's some photos of integrated optics. Basically, these are silicium chip on which there is some waveguide engraved, and the geometry of the waveguides permits to make interference between multiple beams at the same time and obtain some complex visibilities about the astrophysical objects. Next slide, please. Thank you. The integrated optics I use at the moment is a nuller. It uses 4 sub-pupils. Here you have the 4 entries. And what we do is we null the light from the star, the main star, here in between the 3 pairs. And what we do is, so we extinct the light from the star, and then we recombine the null output from this nuller. So we obtain complex visibilities on the light from the companion, that is off-axis, and is not null. So you can see here some pretty fringes I obtained, and if you want more information, feel free to ask. And also, there is a poster from Elsa Huby on the visible version of the first, the visible version of the first instrument that is currently at the Subaru. Okay, thank you.
Hello, my name is Garima Singh, and I work on SKEXEO, which is an extreme adaptive optics system of Subaru telescope. So, low inner working angle phase mask chronographs are extremely sensitive to tip tilt errors, and there was no solution yet to correct for the pointing errors occurring upstream of the chronograph for phase mask chronographs. So, till we developed this solution, which we call a LEO-based low-order wavefront sensor. So in a conventional chronograph, the LEO stop blocks the residual starlight. What we have done is, like, we made this LEO stop reflective, so we reflect all the residual starlight towards a sensor, which is simply a detector. And this reflected light can be decomposed into low-order Zernike modes to measure and to correct for the low-order aberration through single-value decomposition method. And the basic idea behind this sensor is if your post-adaptive optics correction is less than 1 radian RMS of the wavefront error, then the phase aberration occurring upstream of the phase mask is linear with the intensity variation occurring after the chronograph. And so this is the simple theory behind this sensor. So this is a linear reconstructor wavefront sensor. It's fully implemented and tested on SKEXEO bench in the lab. Next slide, please. And what I show you here is the recent on-sky closed-loop on-sky results with this LEO-based sensor. So what you see here is the closed-loop closed-loop residuals for tip, tilt, and focus. So here, this is this is the residuals after the adaptive optics of Subaru closed the loop for tip, tilt, and focus. And the typical value of Subaru's AO loop is like 250 nanometer of RMS, like with good seeing. And this is the residual when I close the loop with the low order sensor, and it really knocks down the residual like to the level of 50 nanometer of RMS. And so you're most welcome to look at the poster number P2 and ask me any question if you have any. Thank you.
Hi everyone, I'm Joyce Van. I'm a graduate student at Cornell University, and my research interest is in automatic optical system alignment and low-order wavefront sensing. And as you can see in the figure here, the black frame shows a perfectly aligned system, and the blue one shows a misaligned system. And we have 2 misaligned parameters here. One is the shift distance, and the other one is the tilt angle. And we derive our equation in simple geometric optic, and we can obtain the final image position in terms of the shift and tilt parameters. And the figure at the right here shows the effect of the shift and tilt parameter to the final image in a single lens system. And as we can see, it will grow almost linearly to the shift polarimeter, but it will grow exponentially to a tilt one. Next slide, please. And the first step of our research is to build a system like this. We will have 2 moving lenses in the middle, and each of them will have 4 degrees of freedom, and they can both move. They can both move along the plane, and they can also tip and tilt. And the goal of this research will be to see if we can build an automated system that can calibrate and align the system itself by using just one CCD camera in the end of the light path. And so our idea would be move the lens independently to see if we can break the degeneracy of the effect of the misalignment of multiple lenses. So if you are interested in this topic, please come talk to me, and my poster is at P7. Thank you.
Hi everyone, I'm Christian de Lacroix, and I am a postdoc at the University of Liège. I work within the Vortex project, so here's a picture of some of the members of our team at the SPI conference in Montreal, trying to create a vortex in the sky. And also, yeah, some of the pictures are related to the papers of some of our members, so I encourage you to read them. And so today I'm going to present the development of a sub-wavelength grating vortex coronagraph of topology guide charge 4, the SGVC4. So as you may know, we recently developed the SGVC2, which is known as the AGPM, and tested it on the laboratory and also on Sky. So here are pictures of the first Sky results with the AGPM, with NACO and the LBT. And here the last picture is the manufacturing process. Next slide, please. And yes, so this slide is a summary of my poster. So now that we managed to fabricate the AGPM, we want to increase the topological charge and to build an SGVC4. So as you can see, the polarization must turn twice as fast to produce the 8 pi phase ramp. So the motivation for our project is to reduce the sensitivity to low order aberrations, but more importantly, with the increased resolution of the future ELTs, the performance of near-infrared coronagraphs will be affected by the finite size of the star, and thus we can mitigate this by increasing the topological charge. So I propose two discrete designs, and I show the first 3D simulations, and I have also a poster. We have several posters, so I encourage you to come if you're interested, and to ask more questions. Also stay tuned because there's more to come in the coming months. Thanks a lot.
Hello, my name is Annie Myrin, and I am a graduate student at MIT working with Professor Carrie Cahoy on a CubeSat deformable mirror demonstration mission. So the purpose of this mission is to flight qualify high actuator density deformable mirrors so you can use them in space on future high contrast imaging space telescopes. So the way we're doing that is to fly a Boston Micromachines MEMS deformable mirror or a similar mirror. There are a lot of different manufacturers on a CubeSat. A CubeSat is just a nanosatellite with a specific form factor that you have to adhere to. It launches as a secondary payload, so a lot of launches are very cheap and or free. And you can get months to years of on-orbit operation data for these mirrors to space qualify them. So our 3U CubeSat is about a shoebox in volume, and half of that is reserved for the optical payload. Next slide, please. So this is an overview of the payload. The purpose of this mission, again, is it's not to do high contrast imaging on a CubeSat. We're just looking at mirror performance and testing out different wavefront reconstruction and control algorithms. So there are 3 different experiment configurations. So there's illuminating the mirror with an internal fiber coupled laser, and looking at with a high order wavefront sensor, looking at mirror actuator displacements. And then using either the internal laser or an external aperture source, we have a focal plane detector to either image a bright star or do focal plane wavefront sensing and correction. So if you have any questions, come talk to me, come find me, and I will see you at the sessions this afternoon.
All right, hi, my name is Ashley Wilkins. I'm a graduate student at the University of Maryland and working at NASA Goddard. So I'm interested, for my thesis, I'm interested in learning about the drivers and the limitations for our ability to detect and characterize exo-Earths with space-based missions and with the new, the next generation of instrumentation, so specifically with integral field spectrographs. So to that end, I'm first presenting a project called Haystacks. It's led by Aki Roberge, who you've heard from a few times this week, where we're putting together a full three-dimensional spectral simulation of the solar system so that we can use that for the purposes of looking at solar system analog. So this is, like I said, a 3D spectral cube, and most importantly, it includes all the sources of noise, background, and confusion that you might have. So this means the extragalactic sources, this means the other planets in the system, and this means also the dust. And so Chris Stark is a big help with that and a big contributor to the dust component. This is available, so we'll use this in our own work, but this will also become available as a community tool in the near future, so look out for that. And then the other project, next slide, please, thanks, is actually working on a prototype integral field spectrograph for space-based missions. So it's called Pisces. It's led by Mike McElwain at NASA Goddard. And it's also, Marshall Perrin is also a key member of the team, so he's here too. Pisces is an integral field spectrograph. It's the baseline, the architecture for Pisces is the same baseline architecture for the AFTA mission, but this is going to be going into next fall, so fall a year from now, we'll be going into the HCIT, the high contrast imaging testbed at JPL, where it can be integrated into their full system and allow end-to-end testing of coronagraph high contrast imaging system, so with the coronagraph and with the instrument in place. And so this will be not only for helpful for AFTA, but for future missions for ATLAST or whatever other architecture you're trying to look at. And of course, the Haystacks model will help inform instruments like this for the future. Thank you.